In question number 5, we are required to actually prove a certain expression starting with this line. And the hint given to us is we are supposed to make use of the factor formulae. So to start with, these two can be combined using the factor formula, which is like this. This is the factor formula that I've used to combine these two terms into this. You can see 2 cos sine. And after that, what I did was I broke this sine t into sine t over 2 cos t over 2, and to break this up from here into here, I've used this formula. This is actually the half angle formula that we are familiar with. And after that, what I did was, because this is a cotangent, right? This is a cotangent t over 2 can be changed into cos over sine. And then a copy of sine cancel with this sine, and it will leave you with just cosine square. And then for the 2 cosine square, I can use this formula, the double angle formula. This is a double angle formula. If you make cosine square t over 2 the subject, you will actually have this one being replaced by 1 plus cos t. And here we are, a proven expression required for 5 part 1. In 5 part 2, right, we are supposed to prove the reduction formula. To prove the reduction formula, what I did was I replaced this integrand using the expression that I've proven earlier. I replaced this whole thing with that statement I've proven in part 1. You can see I've rewritten into this form. Using what is proven in part 1, I've rewritten this integrand into this. And what I did was, after this, I noticed that this is exactly my I of n minus 2. And then for the remaining terms, I broke them up into, I expanded this 1 times with cos of n minus 1t, right, is here. And then cos t times this, and the 2 is actually in the second integral. Can you see? Second integral here, right? So now, if you look carefully, what I want is to just have this term, and the rest of them, I'm sure that it's actually 0. How do I go about showing that the rest of them is 0? Okay, what I did was, this integral, I just leave it. I broke this integral, right, into 2 parts. How do I break this into 2 parts? Okay, 2 cos, right? 2 cos has actually a factor formula you can use. Cos actually comes from half cos of p plus q plus cos of p minus q. So using this red color, I replace this one with this. And now I'm left with I of n minus 2, and then 1 term, 2, and then 3 integral. And you'll notice that for each of them, if you perform the integration for each of them, right, you'll find that each of them will end up with sine something. And then upon putting the limits, you'll find that the last 3 definite integral will all use 0. Right? You can perform the integration yourself. So therefore, what you have proven is, you have managed to prove that I of n is equals to I of n minus 2. And now I bring the I of n minus 2 to the left-hand side. I got this result. I of n minus I n minus 2 is 0. And then in question 5 part 3, you're asked to evaluate this expression. So sine of 2018t cos t over 2, right, becomes the I of 2018. And this can be reduced slowly to become just I4, and then I4 can be reduced to just I2, and you're left with just evaluating I2, and this is I2. Okay, how do you evaluate I2? Okay, so first and foremost, I change the sine 2t. Sine 2t is actually 2 sine t cos t, right? And then I can replace the sine t again into the half angle formula. 2 sine t over 2 cos t over 2, the 2 and 2 give me a 4. Then once again, the cotangent, right? The cotangent can be changed to cos over sine, and then cancel out with the sine. I'm left with cos squared. And the cos squared can be replaced, cos squared t over 2 can replace, in fact, 2 cos squared t over 2 is replaced as 1 plus cos t. And then break this integration into 2 parts. Okay, I want you to notice that 2 times 1 times cos t is this. Then 2 times cos t is cos squared. 2 cos squared t can be replaced by 1 plus cos 2t. It's a double angle thingy. So in the end, you're left with 3 integrands, 1, 2, and 3. And believe me, this first integral and the third integral will end up as just 0. You try integrating yourself and see that so. And then for the middle integrand, right, integral, you integrate to become just pi. And this is how I prove that the answer is just pi. For question 6 is slightly tricky. We're actually asked to prove that in minus 1x minus jn minus 1x minus jnx is equal to something. So what I did is I start off with this line, and by definition of j's, I replace it with the definition. I combine these two together as a single fraction, and I perform some factorization. And I can cancel these two terms, leaving with this, and I integrate it to become just this. And this is what you're required to prove for the 6 part 1. Now that you have this statement, right, you can rewrite this thing into a form of summation, right? Notice that I now change this indices, right, or this index, or the subscript rather, into r and r. So I write this in the form of a summation, summing up from 1 to n. Likewise, on the right hand side, I rewrite in as x bar r and over r, right, and summing from 1 to n also. On the left hand side, if you list out the left hand side, right, if you know the method differences, if you list out all the left hand side, you see that there are a lot of cancellation. Some people call this a telescoping series, or some people say this is actually the method of differences. If you actually were to list out the left hand side and do a lot of cancellation, you find that you'll be left with only j0 and jn. So we have proven that j0 minus jn is equal to summation, right? And this is the expression that they want. That jn is equal to j0 minus a certain polynomial of degree n. And now that we have this expression, jn plus this thing is equal to j0. Remember, we actually have this slide, right? I just simply bring make j0 the make this term. I bring this term. Okay, I'm simply bring this term to the left hand side, so that I can have jn plus the summation is equal to j0, and j0 can be integrated directly. It's just a simple integration to give you minus ln of 1 minus x. Do you realize that actually I didn't put modulus here because there's no need to put modulus for this case since x is between minus 1 to 1. This thing will always be positive. And then now the next part of the question is a bit tricky. I have rewritten jn. You see, I break this t to the power n, right, into minus this whole chunk. If you look carefully, right, this thing on top together minus give you back t to the power n. Why do I break it in this form? The question gives us a hint. They wanted you to have a certain expression of 1 minus t to the power n, right? So I make it happen. And now I break this into two integration. This first one, and then minus and minus give you a plus. This is the second one. And this second integration can be integrated quite easily, right, to give you this expression. And for this one, it's actually a GP, 1 plus t squared until t to the power n minus 1. You can try applying the GP formula. Right? Just a GP. You apply GP formula and find that it's exactly this thing inside. And then if you were to integrate them term-wise, you integrate them term by term, and then put in the limits, you find that you actually get this. So what I've proven is Jn, I bring this thing to the left hand side, okay? Jn plus this summation, which this summation is actually this whole chunk. This whole chunk I brought to the left hand side is equal to this. It's the same result that you have gotten in the earlier part. And now we want to actually do the last part. From what we have here, right, I'm just rearranging the terms. I now have this summation equals to this. And then now I take limits throughout. And then the question tells us that the limit of this thing exists and is equal to 0. I can break this into the difference of two limits. And this expression here, is independent of n, right? So it just stay as minus ln of 1 minus x. And this other one we are told is 0. So in the end, you're left with that this summation is equal to this. And I want you to notice that actually this is exactly, it actually tallies with that Maron series for ln of 1 minus x. You can try experimenting, no? put in the Macron series of 1 minus x into here, you find that it'll be equals to this summation. Okay, that is actually tutorial 3.2, question 5 and 6.